Okay, dear students, today we will learn something about the magnetic susceptibility of diamagnetic materials. Here, the topic is Langvins theory for diamagnetic materials. So, what this theory tell us and how he can use classical mechanics and calculate the susceptibility for diamagnetic materials. So this theory is based on classical law. There is also one more approach, quantum approach, due to which we can calculate the magnetic susceptibility of diamagnetic materials. But here in this case the classical law is used, and I am already telling you what diamagnetic materials are in previous lecture. Here you have to calculate only the magnetic susceptibility, and that is denoted by chi. Chi is called as magnetic susceptibility. So I am already telling you what this magnetic susceptibility means in previous lecture. So this is actually the number of induced dipole moments per atom, that is called as magnetic susceptibility. But and also I am telling there this magnetic susceptibility is related to the magnetization as m upon h, that is the h's magnetic field intensity. So here it is also magnetization, here it is magnetic intensity, that means it is a dimensionless quantity, dimensionless quantity. So I repeat here the previous lecture because we are familiar with the magnetization, how this magnetization in different materials, in every material can come, because there are dipole moments present in every material, because three motions are responsible for that dipole moments. One is the orbital motion of electron around the nucleus. It acts as a current carrying loop. So this current loop has magnetic moment. So it acts like a tiny magnet having north pole and south pole separated by some distance, like this. If this is north, this is south, and this is a tiny magnet. These tiny magnets are always present within the material because of orbital motion of electrons. And the second motion is electron spins in its own axis, about its own axis, that also will give rise to the dipole moment in a material. And the third one is the nuclear spin, that is spin of electrons, spin of neutrons and spinning of protons within the nucleus will also participate in the atomic dipole moment in the material. So these three motions are responsible for creating dipole moments within the material, every material. But here you see the diamagnetic materials, because diamagnetic materials are those materials which tend to move from strong magnetic field uh, to weak magnetic field, because it is repelled in magnetic field. So this is based on the classical law. So we can write, because when electron moves around the nucleus in a circular orbit, the forces are responsible for maintaining this orbit. The first one force is the centripetal force, which is necessary, which is given by the Coulomb force between negatively charged electron and the positively charged nucleus. So this Coulomb force will provide the centripetal force for electron, and there is another force that wants to move, that tends to move this electron from its orbit, that is called as centrifugal force, which arises itself, and these two forces will balance each other and maintains the circular path of electron around the nucleus. So here we use the simple classical mechanics, and the centripetal force can be written as m omega square r will be equal to z e square upon 4 pi epsilon naught r square. This is the Coulomb force. Here it is centripetal force. So centripetal force will provide the Coulomb force for electron for maintaining the orbit. The parameters like omega is the angular frequency, m is the mass of the electron, r is the radius of the orbit, and Ze is nuclear charge. So we are familiar with these parameters in electrostatics. So there is no need to define these parameters here. So we can write this. This is the equation. Or from this equation we can calculate the omega, that is angular frequency, will be equal to z e square upon 4 pi epsilon naught r square m, that is r cube m, because r and r will be r cube here. So this is the necessary, this is angular frequency under root. This is the angular frequency, value of angular frequency with which the electron revolves around the nucleus. So this is all in absence of the any external field. When we apply a magnetic field for diamagnetic materials, there is another force acting upon an electron. That force is called as Lorentz force. In presence of external magnetic field, electron will experience Lorentz force. So Lorentz force, we are familiar with this force, that will be equal to F will be equal to m omega naught square, that will be equal to E V cross B. V is the linear velocity, B is the magnetic field flux density. So we can write it as F will be equal to A VB sine of theta, because A cross B will be equal to AB sine of theta. This is the cross product of two vectors. And we can also written it as F will be equal to AVB sine theta, for theta will be equal to pi by 2, that is 90 degree, because if this is the magnetic field B, here this is the, sorry, this is velocity of electron, and this is the Lorentz force F. So this is perpendicular at 90 degree if it is angle theta, angle between B and B. So here the Lorentz force will be in perpendicular to this plane, that is pi by 2. So here we can write F equal to AVB. So this is linear velocity. Linear velocity will be related to angular velocity r omega. So it can be written as F will be equal to A r omega b. So this is the equation. So we can write the angular velocity relation as, here you see m omega square r will be equal to m omega naught A r omega b minus m omega square omega naught square r. This is the centripetal force will be equal to this Lorentz force minus m omega naught square r. Sorry, we can write it as m omega naught r square minus Lorentz force. Lorentz force is E omega r b. So this is the right equation, and from this equation we can simplify it as r square is here, r square, sorry, m omega r is m omega r, m omega square r. So they are cancel each other. ठीक है? So after that we can write omega square, this term will be in this side, that is plus a b upon m omega, because m is divided here, plus minus omega naught square, m and m cancel each other, will be equal to 0. So this is the equation, right equation. Here you see this is quadratic equation in omega. So it will give us value for omega. Omega will be equal to minus b, that is eb upon m, plus minus under root of b square, that is b eb upon m whole square, minus 4 ac, that is plus 4 omega naught, divided by 2a, that is only 2. So omega will be equal to minus b, this can be written as plus minus under root of eb upon EB upon 4. This can be written as EB upon 4m 2m whole square plus omega naught minus EB upon m. This is the value of omega. So this equation will give us omega will be, it can be, because omega naught is the angular frequency of electron in presence of magnetic field. Omega is the magnetic field. This is the original frequency. This is in presence of magnetic field. So here you know EB upon 2m is less than, here it is omega square, here it is omega square, less than omega naught. So if it is very small, then square of this term will be neglected here. So that there remains plus minus under root of, not under root of, because omega naught square, that is omega naught square. Naught square, because square and root cancel each other, omega naught minus EB upon m. So this is the angular frequency for electron in presence of magnetic field within the material, the diamagnetic material. So here you see there is additional term, that is EB upon m. EB upon m, that means 2m, EB upon 2m, because 2 is multiple here, that is EB upon 2m. So EB upon 2m is the change in frequency. This is change in frequency, and there is a change in frequency, omega naught minus this term. So EB upon this is also dimensions of frequency. So there is change in frequency, omega naught minus this frequency. There is a change in frequency. This change in frequency will give rise to additional dipole moment within the material. In absence of magnetic field, there was dipole moment is present within the material, but they are in random direction. But when we apply external magnetic field, there is a change in frequency of electron. This will create additional current, and this additional current will create a dipole, magnetic dipole moment within the material. So the change in frequency delta omega will be equal to minus EB upon 2m. So this can be in linear relation, 2 pi delta nu will be equal to minus EB upon 2m. This is not V, this is nu frequency. So delta nu will be equal to minus EB upon 4 pi m. This is the change in linear frequency. This change in linear frequency will relate to the dipole moment. As per the relation, you know the corresponding magnetic moment. The corresponding magnetic moment will be equal to delta m is equal to current into area. This is the basic definition of the magnetic moment. Here you see delta m will be equal to, current will be equal to, by definition it is equal to charge divided by time, that is charge of electron divided by time period multiplied by area will be pi r square, that is the area of the circular loop. Here delta m will be written as this, so delta m can also be written as 1 upon t is equal to frequency, and nu is related to 1 upon t, so that will be equal to delta nu is here, that is minus e square, e square b upon 4 pi m into pi r square, pi and pi goes, so there remains delta m will be equal to minus e square b upon 4m r square. It can be written as delta m will be equal to minus e square b upon 4m summation of r square. If it is summarized for all the electrons present in the material, overall z orbital electrons, z overall z orbital electrons, this can be written as delta m will be equal to minus e square b upon 4m z r square. So this r square is there, this r square is average distance, actually average distance of electron from field axis. If it is the circular orbit, this is x, this is y, and this is z axis. Here it is x axis, this is y axis, and this is the r through which the magnetic flux density, magnetic field can be applied. So in terms of xy plane, this is perpendicular to that, we can write it as r square mean average will be equal to x square plus y square. If x will be equal to y, then we can write it as r square is equal to twice x square, right? So here we can define another distance, that is r naught. R naught is the average distance from nucleus of electron from nucleus. We know the nucleus is a spherical, that is it is a three-dimensional, so that is r naught average square will be written as x square plus y square plus z square. Here also, if x equal to y equal to z, we can write r naught square is equal to 3 times x square. So the relation between r naught and r can be calculated as from these two equations. If it is equation first, if it is equation second, then from equation second and first and second, we can write r naught square is equal to 2 upon 3 x square. 3 upon this r square. This is r square, this is r naught here. Therefore, we substitute this value in this equation, magnetization equation. Then we can write delta m will be equal to minus E square B upon M 4M Z into 2 divided by 3 R naught square. Delta M can also be written as in simplified form E square B upon 4M Z, that here it is 6, not this, and 2 4 that is 2 3 is 6, and R naught square. So this is the correct equation for magnetization. So we know the basic definition of, because we have to calculate the magnetic susceptibility of the material, that is related to the magnetization as chi will be equal to M upon H. So here magnetization is minus E square B Z 6M R naught square. So it can be written as minus E square B Z upon 6M into R naught square, and H will be equal to mu naught B. H, magnetic field intensity, is related to magnetic flux density B as, and mu naught H will be equal to B. So here it is B upon mu naught. B and B cancel. So we can write E square Z mu naught R naught square divided by 6M. That will be equal to magnetic susceptibility. If there are n atoms, then multiplied by n here. So this is the equation for diamagnetic susceptibility. So here you see it is negative. I am already telling you magnetic susceptibility for diamagnetic materials is always negative. Here it is negative. That means it is because it is recovered in magnetic field, external magnetic field. So if we, E is the charge of electron, its value is known, mu naught is known, 4 pi into 10 to the power of minus 7. Electronic charge is 1.67 into 10 to the power of minus 19 coulomb. M is the mass of electron. So all these parameters are known. R naught will be, if R naught will be equal to 0.1 nanometer, that is 1 into 10 to the power of minus 10, that is 1 angstrom. That is 1 angstrom. So the calculated value for diamagnetic susceptibility will be minus 3 into 10 to the power of minus 6. 10 to the power of minus 6. So it is dimensionless. Negative भी है but dimensionless quantity. So this is the diamagnetic susceptibility for diamagnetic materials. Similarly, we can calculate the magnetic susceptibility for paramagnetic materials, similarly for ferromagnetic materials. So all these, I hope you understand well. Thank you.